We're going to go through chemical nomenclature rather quickly in this video. Obviously, you have the opportunity to pause and rewind if you need to, but this is going to be one of those videos that you'll probably come back to several times over the course of this unit to refresh your memory on how we do the different naming of chemical compounds. We're going to learn a system for naming. However, we want to keep in mind that we will come across several common names that have kind of stuck over time. For instance, water has a common name, ammonia, NH3, methane, table salt, NaCl, and table sugar. So kind of expect that we may see some things that have both systematic names and common names. The system that we use for naming a compound depends on the type of compound that it actually is. Now, to determine the type of compound, what we need to do is ask ourselves what type of bonds hold the atoms together. In a kind of general sense, what we need to do to answer that question is identify the type of elements that are being bonded together. If we look at our periodic table, we have two general choices. We have metals, metallic elements, and we have non-metallic elements. So that gives us three possible combinations. So the first combination would be if we took a metal with a non-metal. So we took an element from the left side of the table and combined it with an element from the upper right side of the periodic table. The second combination would be two nonmetals. So a nonmetal with another nonmetal. And then our third possible combination would be a metal with another metal. The metal with another metal tends to be fairly simple. It's just going to be the metal name. So for instance, if we have a iron or copper atoms all together making metallic bonds, we would just call them by their metallic name. The other two, we're going to have the other two options, metal with nonmetal and nonmetal with nonmetal. We're going to have some different options for naming those different systems. The type of bond that's going to form is going to reflect how each type of atom tends to deal with its electrons. So metals tend to lose electrons. In other words, they have electrons that tend to be rather loosely held, and nonmetals tend to gain electrons. So if we looked at it from a kind of a generic metal with a nonmetal, we would have an electron going from the metal being transferred to the nonmetal. What this creates, once the metal loses the electron, we are now going to have a particle that is charged positively, because there will now be more positive than negative charges. We call that particle an ion. And likewise, the nonmetal, when it gains an electron, it will then take on a charge that is negative. So it would be a negative ion. And positives and negatives, hopefully we've learned from science courses prior, that positives and negatives will attract. This attraction between the positive ion and the negative ion is called an ionic bond. So the bonding that happens between a metal and a nonmetal is called an ionic bond. Notice that when we form an ionic bond, we are also forming ions. And so that's kind of an important point for us to realize. So when I look at something like sodium chloride, sodium being a metal and chlorine being a nonmetal, the formula for that would be NaCl, and we refer to this as a formula unit. Okay, so the NaCl would be the formula unit. Now, if we look at a nonmetal with a nonmetal, Nonmetals, as we mentioned, tend to gain electrons. But now we have two atoms that both tend to gain electrons. So how is that going to work? Well, say we take two hydrogen atoms, and both of them will contribute an electron to be shared. And we would draw a picture something like this, and we'll get more opportunities to draw these kind of pictures. But what happens there is the nuclei on both hydrogen. So I'm going to draw the nucleus for each of the hydrogen atoms. And then I'm going to draw the electrons that are being shared. These electrons are going to be attracted to both nuclei. Given that they're being shared and they're attracted to both nuclei, in order to have this happen, those two atoms have to stay together. So that's the nature then of a covalent bond. So between two nonmetals, we're going to end up with a covalent bond. Now in this case, we're going to form molecules. So recall over here on the ionic side, the metal and nonmetal, we form ions. Over on this side, we're going to form molecules. And an example of this would be water. And here, H2O could be referred to as a molecule. And recall that over on the ionic side, we refer to that smallest formula of the ionic compound as a formula unit. Now, to try and create like a little bit of a shorthand here, what I often allow, what we'll do in class to understand this is an M with a circle means molecule, and an F with a circle around it means formula unit. And by the way, an A with a circle around it would obviously mean atom. All right, so let's take a look at the covalent compounds first. Covalent compounds are going to be a little bit simpler to deal with. They simply use a prefix system. So over on the left here, we see our prefixes that we're probably familiar with in geometry: mono, di, tri, tetra, pent, hex, hept, oct, non, dec, going from 1 all the way up to 10. A couple of common compounds then that we're probably familiar with: a CO2 and a CO. The top one would be carbon dioxide. Sorry about that. And the CO would be carbon monoxide. So as you can see, the di prefix for the two oxygens in carbon dioxide, and the mon prefix in carbon monoxide for the one oxygen in there. It's important to understand, too, that you notice that you do not see the mono in front of carbon. So if the first element is a single atom, then you would leave off the mono part. It's understood there. And other covalent compounds will have similar naming conventions. Ionic is going to be a little bit trickier. When we look at ionic, remember that an ionic compound has two parts. It has the positive ion part, which is the cation, and it has the negative ion part, which is the anion. Naming a covalent compound simply involves just taking the cation name putting that down first, and the anion name, putting that down second. So for instance, if you looked at NaCl, the metal part here is sodium, and the nonmetal part is chlorine, although we will change that second element, the anion, we'll change the ending of that to "ide." So we'll talk a little bit more about that in just a moment. You'll notice that we did that as well in the covalent system. Up here, the second element took on that "ide" ending as well. All right, so the cation part. From the simplest standpoint, this is just going to be the metal name. And the metal is always going to be listed first in the ionic compound. Now, we also have kind of a slight problem with metals that have multiple, what we call oxidation states. These are metals that will lose different numbers of electrons depending on how they react. So for instance, we could form a compound between iron and 2 atoms of chlorine, and we could form a different compound between iron and chlorine that had 3 atoms of chlorine for every 1 atom of iron. The way that we name this is iron 2 chloride, and this would be iron 3 chloride. Now, it's important to realize that these Roman numerals do not refer to the number of chlorines that are bonded to the iron. The Roman numeral refers to the charge on the iron. So for instance, in the FeCl2, iron has lost 2 electrons, so it has a +2 charge. In FeCl3, the iron has lost 3 electrons, so it has a 3+ charge. So again, it's important for us to realize that that Roman numeral refers to the number of electrons that were lost. So here's a list of elements or metals that we have multiple oxidation states that we're going to be using quite frequently in class. So you need to know these. In addition to iron, you have copper. Copper will take on a 1+ charge or a 2+, meaning it will lose 1 electron or 2. Cobalt can lose 2 or 3 electrons. Tin and lead both have the option of losing 2 or 4. And mercury is kind of unique. A single mercury atom can lose 2 electrons and become a HC2+. Or if you have a combination of 2 mercury atoms together, the 2 atoms together lose a total of 2 electrons and you get a 2+, but there's 2 mercuries together. So we'll work with some of those in class just to clarify them. All right, the anion part. So remember, the anion part is the negative ion. The negative part, the part that gains the electron, which is typically the nonmetal. So if we have a single element gaining that electron, so for instance, chlorine. If we have a single element gaining the electron, all we do to name this is we take the ending off and we add IDE. So chlorine becomes chloride. And we could very quickly go through all the nonmetals that would do this. Oxygen becomes oxide, fluorine becomes fluoride, nitrogen becomes nitride, sulfur becomes sulfide, phosphorus becomes phosphide, bromine becomes bromide, iodine becomes iodide. And that's pretty much it. So those are all of your single element anions. Those are all the nonmetals. Unfortunately, we have a number of polyatomic anions. And polyatomic anions, as the word poly means, many. So we're going to have more than one atom acting together as the anion. So one of the most common is an ion composed of 1 nitrogen and 3 oxygen, all together with a -1 charge, which means those 4 atoms all together have gained 1 electron. And the name for this is nitrate. Okay, and there's going to be several of these. You'll get a handout in class that will list the ones that you need to know. So don't get too worried about these. We'll do a lot of activities in class so you can learn them. And you know, learning of these, you can do them in kind of a systematic way. The other one that looks similar to this is NO2 with a minus, and this one is referred to as nitrite. Okay. So we will have to do, you know, some memorization of these ions, but again, we can do that in kind of an organized way and make it not be quite as bad. The final part in this segment is going to be just how to go from the name to the formula in kind of an efficient way. You'll learn how to do this a little faster. You'll develop your own kind of techniques for this. But for instance, if we do, remember we had iron, oops, excuse me. Let's say we have iron 3 oxide. All right, so iron 3 oxide. So what we want here is for the iron to be a 3+, which means that the iron is going to lose 3 electrons. Oxide is oxygen with a 2-. So the oxygen wants to gain 2 electrons. Well, obviously you can see that if you put 2 of the, or 1 of each of these together, it's not going to work out quite right. So the way that I like to do this is to take the metal and say, all right, well, my metal, iron, wants to lose 3 electrons. And then I take a look at my nonmetal, my oxygen, and I know it wants to gain 2. So there's 1, there's 2. Well, where's that other electron going to go? Well, we're going to need another oxygen atom. So that one's going to go to that oxygen there. However, that oxygen actually needs 2 electrons. So I'm going to need another one to make that oxygen happy. Where am I getting that 4th electron? Well, obviously from another atom of iron. But that atom of iron doesn't want to lose just 1, it wants to lose 3. And you can kind of see where this is going to go. Where are those other 2 electrons going to go? Well, obviously they're going to go to another oxygen atom. And now when you count these all up, you have 2 irons and 3 oxygens. So you can come to the conclusion that iron 3 oxide would have the formula Fe2O3. So and again, you can see here that the Roman numeral in the iron 3 doesn't refer to how many oxygens it combines with. It refers to the charge on the iron. So that's it for your basic ionic compounds and covalent compounds. We will have to do a separate video on the naming of acids, but we'll do that later on. So. And again, remember that we will practice these, so don't get too too concerned at this point if some of this went a little fast for you.